All right, so we've got our second midterm coming up on Monday. So that'll start where the last one left off. So that'll start at couples, which are pure moment with no associated force. Couples have the same magnitude anywhere on the object. Distributed loads, find the area of the loading diagram, apply it at the centroid. The centroids are shown on your formula sheet if you need them. For a rectangle, it's midpoint. Triangle, it's what I call the third point for a right triangle. Third of the distance over from the right angle. 2/3 of the distance over from the vertex. We got composite loading diagrams, cut them up. Okay, resultants there, we got the different formulas for all that. Sum of fx, sum of fy, sum of moments. And then the resultant force is found by theorem of Pythagoras, and the angle of the resultant is found using arctangent, y over x. You can find those offset distances too using those moment divided by force equations. All right, then 2D equilibrium, start with a free body diagram, use sum of fx, sum of fy, and sum of moments to solve. Okay, now probably what you want to do on those, the general approach is to figure out a point about which you'll take moments. Generally that point is a point that has two unknowns going through it. Then dimension from there, get x and y dimensions to all the forces and reactions, and then take a moment equation to solve for the remaining unknown force. Because if you take a moment about a point with two unknowns, there can only be one more unknown if you're going to solve it with statics. Okay, so you'll find the x and y dimensions from the point you're taking moments about to all the forces and reactions, and do a sum of moments equation. Remember to include moment arms. That's a common mistake people make. They forget to include those. If your answer seems way out of whack, quite often it's because you might have forgotten moment arms, so that might be something to check on that. Okay. 3D equilibrium, start with a free body diagram. You got 6 equations to use. You can use a 2D approach or a 3D approach. Or excuse me, a 2D approach or a vector approach, either one. Trusses method of joints, find the reactions first, draw a free body diagram of each joint. Okay, and then sum of fx equals 0, sum of fy equals 0 for the joint. Okay. Members are all in tension, which pull on both joints, or all in compression, which push on both joints. 0 force members, you've got to prove at a joint that sum of fx is 0 or sum of fy is 0. I show some typical 0 forces there below. So you see you got unloaded corners with 2 members, unloaded T's with 3 members, and then that collinear force corner there, the odd member that does not support the force could often be 0. Okay. And then method of sections, which we'll finish up here today. And then I got some old test problems, you know. We can go over these Friday maybe or something if you want. Right? So that's what's coming up Monday. Yes?
How many questions will be on the test?
I don't know. It'll be kind of similar in form to the first one. So 5. Maybe. I'm just talking off the top of my head. I haven't made it up yet, so I don't know, but something around 5. You know, it'll be similar to what you got on the first midterm.
Will be similar to the review we have.
Yeah, I don't know. I'm going to have to go. I'll legal line you down and say my attorneys advised me not to comment on that question, so I don't know. And that is one thing, you know, don't just do the review and say, yeah, I got it. I mean, you know, look at the list, because I never can fit everything on the test, so I can pull anything off of that list. I can tell you for sure there'll be a 2D equilibrium problem on there. There'll for sure be a truss. You know, there is a a certain connection between the length of time we spend on things and whether they show up on the test is or not. So I think that, there'll certainly be a truss problem on there. There'll certainly be a 2D equilibrium problem on there. I'm sure you'll have some distributed loads, because we've been using those a lot. Okay. Same sort of drill as before, I try and create 70% of the test being basic stuff, extra 15, 20% being a little bit more advanced stuff, and then maybe something a little tricky there for the last 6 or 8%, same sort of thing. So use your time wisely when you're doing the test, look at how many points something's worth and gauge your time to that. And, if you got to cut and run, that kind of thing. All right. We're good with that. Everybody has a copy, all that stuff, or good? All right. So we'll cover that. If you got any questions tomorrow, I could take them, or Friday. We'll go over that review on Friday if people would like. Okay. Now we got one other way to solve out these trusses. So let's have a look. This is the method of sections. So what you do on this thing is you find the reactions on the truss, like you always do, and get the angles. Now what you can do with method of sections is kind of go in and solve for 1 or 2 or 3 members inside the truss without having to do the whole method of joints to get there. Method of joints is very reliable. However, it takes a lot of time. Okay. Now, you can't always do method of joints either. You'll notice on this particular truss, see what I call those X panels? A, B, C, D, E, and then on the other side we got G, H, I, J, K. You can't get through those with method of joints. It just can't get there from here, sort of thing. So, there are certain problems where you might need to use method of sections. So we're on 530 is where we're at. Okay. All right. So what you do is you figure out first you find the reactions. And we went ahead and did this on 530. I've got it circled in there. So we started with that, okay? And then what we do is we cut through the members we want to solve for. So on this particular problem, on the top in the problem statement, we want to solve for FD, FE, and EH, those right there. Then what I do, I take an imaginary saw and cut through any of the members I want to solve for. On this problem, it's nice and easy. I can just cut vertically there between D and F, and I'll cut through all 3 of them, okay? Now, the theory on this is that if the whole truss is in equilibrium, any part of the truss is in equilibrium. So this part of the truss right here, this rectangle, is being held in equilibrium by the reaction and the applied force, but also by the forces in DF, EF, and EH. Okay? All 5 of those things work together to hold that thing in equilibrium, just like any sort of equilibrium problem we've done. So what we can do is use statics and solve for some of the forces in the members, DF, EF, and EH. So I cut through the truss, I throw away 1/2 of it, say that half, and then I work with the left-hand side only. And when I cut through those members, they can be represented as forces on that little rectangular panel there on the left-hand side. So on AB, ED there, I've got those 3 members pushing or pulling on that thing that help hold it in equilibrium. I represent them by forces. I know the angles at which they act. I've already found the reaction for the whole truss, which are independent equations. So I've got that 6400. I've got the applied 6000 up at D. And I'll notice when I look at that thing, I've got 3 unknowns, so I can solve that with statics. See? All right. So that's basically how you do this method. All right. So I can solve for those 3 unknowns with statics. I make them unknowns by cutting through them, at least in my mind's eye. And they're part of what's holding that rectangular section there to the left in equilibrium. So if I were to give you an equilibrium problem with a, with a force, a vertical force at B, up and a vertical force at D down, and then these three forces on it, I think you could solve it. You know, what would be the first thing to do if you want to solve for those three forces? Where would you start? Yeah, I think a moment around, I'd probably go around E, yeah, because you got two unknowns acting at E. You could solve for that top force on the top, okay? So off you go. It's just another equilibrium problem once you get it down, once you do all these steps to create this drawing. So you got any questions on that stuff? Doing all right? Okay. Oh, actually, I started with a sum of Fy. I only got one Fy force, so I did that first. So, okay. So I got 6,400 up, 6,000 down, plus sine of 53.13, which is the angle of EF, times whatever EF is. And the sum of those three equals 0. So I get 0 is 400 plus 0.8 FEF. So 0.8 FEF is negative 400. So FEF is negative 500. The negative means it's not in tension, as I assumed, it's in compression. So FEF is 500 newtons compression. So in this one, I only had one Y unknown, so I just started with a sum of Fy. All right. So that gets me the first one. Now to get the next one, I think I could take either moments about E or D. I think I took them about E. You could do it either place now because we've already solved for EF. I'd probably take moments about E because I'll have one less term in the moment equation. I could just, so I'll just have the 6,400 and the FDF, I think, if I take moments about E, because everything else goes right through E, okay? Even the 6,000 up at D goes through E. So that's the next thing I do. If you take moments about there. Now I know EF, it's 500 down and to the left, but I'll take moments about E, and I'll get negative 6,400 times 2 meters because that's going clockwise, so that's why that's a negative, right? So what I'm doing there, I'm doing that times this moment arm right here. So that's where that comes from right there. And that's a negative because it would go clockwise. And then I've also got this other one that I want to solve for, FDF. And that'll be times, what, 4 meters there. See, that one's negative too because it's clockwise as well. So I can take the 40F to the other side of the equation and multiply 6,400 times 2 and get 40F is negative 12,800. Divide by 4, I get FDF is 3,200 newtons. And that's compression now for FDF. So again, I got a negative on that one. The net meaning of the negative is it doesn't pull, it pushes. So we're doing all right. Yeah, question there?
On the test, would we be drawing all these joints to regarding diagrams? Or is that only on certain problems?
Oh, on method, well, I really don't specify what all you have to draw. I mean, I don't know, have I done that in the past? I mean, maybe on method of joints I would, just because I'm trying to help you really. Now on this thing, yeah, I know it gets to be a little onerous drawing all this stuff out.
So you'll tell us if we have to.
Yeah, I will. Yeah. Okay. So now we get to FDF. Again, I got a negative answer, so it's in compression too. It pushes on D. So we good with that? Okay. And then we got one more, FEH. Why don't you find out what FEH is? See if you can get that. We'll be looking for about 3,500 on this one when you get it. All right, now, the thing on this stuff is, don't make it more than it is. That's just the statics problem. That's all that is. If I give you a little rectangle with those 5 forces on it, I bet you can solve them out. What's the quick way to get what you want? What's the simplest equation to get it with? Yeah, I think what we got going on there, that thing's pulling to the right, correct? We just don't know what it is. So some of fx, see? That's the quick way to get it, right? So I wouldn't be doing a moment equation on that because it'd just be more complicated, more work, more tendency to, more time, more work, more chance for error. So I just do a force equation on that one, okay? So you gotta identify what you're looking at. And again, it's just a statics problem, that's all it is. There's nothing fancier about it. I know we've cut a chunk out of a truss, but don't get hung up on that or anything. Once you've done that, it's just a statics problem. And you know FDF and you know FEF. So there's only that one unknown left. You all good with that? Going some FX? Any questions on it? Yeah, you're looking for 3,500 is what you're looking for. You might have some. Yeah. 3,200 is going in the Well, let's see. I don't know if I do that. Just take this figure. And just sum it with x. 0. Let's just see quicker. Joints are going to have awful lot of stuff.
So notice you're not including the RAX in this separate. The B joint. Why is that?
Why am I not including RAX? I think RAX is 0 on that. There is a pin joint there, but there's no applied X force. So, the X reaction, I think you meant BX, right?
Yes.
Yeah, it's 0. So that's why it's not on there. There isn't one.
And how do you know there is one?
Well, there isn't one because there's no applied forces to begin with in the X direction. So if I go sum of FX for the whole truss, it'll just be 0 equals R BX. I guess, did I write that as AX? I guess I did. Or does that a B? I can't tell, but it's 0. It zeroes out. Okay. Yeah. Okay. So we're getting something like that. So that's the basic idea of this stuff. You just make a cut through a member you want to solve for. Well, I guess first you find the reactions. You always want to do that because if you don't have the reactions, you're going to have too many unknowns to really solve. Okay, so find the reactions for the entire truss first, and then identify the one you want to find, make a cut through it, and then write up statics equations for one side of the truss or the other. You're going to cut through and take one whole side or one whole other side. Okay, so I took the left side. So essentially I threw the right side of the cut there, the stuff to the right of the cut, I just threw it away. I don't care about it. I'm just dealing with the left because I know the left is in equilibrium. Any piece of that truss is in equilibrium, then I'm using the left. Okay. Yeah, question?
I guess I'm still unclear on how you got the 32 grade.
Yeah, I did a moment about E.
Right, okay.
So I needed that, and I had to go through those steps to get that. So I'm just, you good? Earn that? Okay. All right. So now another little rule on this is you can't cut through a joint because that creates an ambiguous situation. Cut through members. Can't cut through a joint because then you're not sure where to assign forces exactly. You know, if you cut a joint into two pieces, it becomes ambiguous what's going on there. So you cannot cut through a joint. You've got to cut through members. Okay. Yeah, question?
So at the joint, you're not analyzing anything at E, because everything to the left of E, you're saying is not involved in what's happening.
Yeah, E is just a point where forces are applied. So I'm not like pulling E out or anything. It's just part of that rectangle.
Yeah, because if you're analyzing E, then you would say there's an X component and AE.
Yeah, see, the method of joints is a special case of the method of sections. You could, method of sections is how you always do trusses. If you do method of joints, your section is a particular joint. Here, I'm not doing a particular joint. Here, I'm cutting off, I'm using a piece of a truss as what I'm cutting free. All right, so we good with that? I mean, that's the basics of this method, is to do it in that way. All right, now there's a few little tricks on this stuff. Why don't we look at the tricks here? Let's say we've got a truss that kind of hangs there. That's on the next page. 540. And let's say we want to find the force in BC. Okay, so what you would do is find the reactions, and I went ahead and did that. So I went moments about point F, and I got RA is 6750. And then I did sum of FY, and I got RE is 4250. Okay, so always find the reactions when you're doing this. If you don't, you're just going to have too many unknowns to do much with when you start making cuts. Because generally speaking, when you make a cut, generally speaking, you've got at least 3 members that you cut through. So you can't have other unknowns floating around out there. It's just generally speaking. Now there's exceptions to that, but that's the general rule. Okay, so I get the reactions. Okay, now I want to find BC. The obvious thing to do is to cut where I'm showing there, okay, right here. So I'll get a free body diagram that looks like that. Now, when I make that cut, I get 3 unknowns, AC, BC, and BD. Okay, so, and notice that 2 of the 3 are angled. So what I'm going to have to do here is, if I want to solve this quickly, which I might want to do, what I would do is I would find a point where 2 of the unknowns intersect so I can solve for the 3rd. Okay, so the point that I would use there would be point H, which is not even on the truss, but that's legal under the laws of physics there. I can take moments about any point I want. Okay, so what I can do is I can say, okay, when I make this cut, I've got these 3 unknowns, AC, BC, and BD. I want to find BC. So if I'm going to do that, the quickest way to get it done, now there's other ways, but if I'm in a hurry, what I'm going to do is take the point where 2 of the unknowns intersect, i.e. the other 2 unknowns. So if I can figure out where BD and AC intersect, That's out here at H, okay? I could take a moment about H. And doing that, I can solve for BC. So if you're in a bit of a rush or you just want to show off or whatever you're doing, you could find that point, okay? Now you could go through it, you could do it other ways. You could take a moment about B and solve for AC. You could, there's other ways you could do this, but it might get a little, take a bit of time and involve a lot of calculations. So the quick way to get in there and get this done is just to figure out where that point H is at, okay? And it shouldn't be too awful bad because I know that AC is horizontal, and then I can figure out the slope of BD. BD drops 0.2 over a run of 0.6, okay? So there's the slope of BD. What I want to do is figure out when that gets up here to this horizontal line, how far over will it intersect the horizontal line? That's what I want to figure out. Okay. Now the horizontal line, it has to go 0.6 meters up. So that's the rise, you might say. And the run is the unknown, x. So what I'm going to do, I'm going to set my known slope, my negative 0.2 over 0.6. That's the slope of BD. And I know I want that rise there to be that negative 0.6. So I want to solve for x. Okay. And I just set those equal. So I'm just setting two slopes equal. And I'll just cross multiply to solve that. Okay. And I'll solve for x. So I can run the numbers on that. And let's see here, let's run the numbers on that. So when I run the numbers on that, what's going to happen here, I'm going to cross multiply that thing. And I'm going to get negative 0.6 times 0.6. So that's negative 0.36. And that's going to be negative 0.2 times x. Okay, and then if I divide that out, am I going to get 1.8? Is that what I'm going to get? I think it is. Okay, so x is 1.8. Okay, so if I project that line BD, by the time it hits that top horizontal line that starts at A and goes over horizontally, it's going to run 1.8. That's what it's going to do. So that's x. All right, and now I can use that and take moments about that point now that I know where it's at. So what I'm going to have then is I'm going to have, when I take moments about that point, is 6750. This is 1.8, so that leaves this distance right here at 1.2, right? 1.8 minus the 0.6 leaves 1.2 there. So I'm going to have 6750 times 1.2, and that'll be counterclockwise. And then I'll have this 8,000 times 1.8. That'll be clockwise negative. And then I'll have two components of FBD, cosine 45 for the x and sine 45 for the y. So cosine 45 FBC will get me that horizontal component. As that cuts under my point H, that'll go counterclockwise, so that'll get a positive. And that moment arm there is 0.6. Okay. And then I'll also have a sine 45. So sine 45 will go that way, up. That'll have a moment arm of 1.8. And that'll go counterclockwise too, so that gets a plus. And so then I can run the numbers on that, and I can solve for FBC. It's 3712. Okay, so that's one way to solve for that. There's others, okay? This is just the quickest way. okay? Now, we get a lot of terms in that equation, 4 terms. We good with that? Okay. All right. Now, if I really want to get tricky there, I could actually take FBC, the unknown, and slide it up to point C, even though that's not on my cut of the truss, but I could do that, and that would get me a simpler equation. It changes the moment arm, it's 2.4. But what I would have there would be this component of force, which would be sine 45 times whatever FBC is. And that moment arm there would be 2.4. So you could do all sorts of little tricks on these things, to solve them out. That just gets to the answer again with one less term. So instead of 4 terms on that in that equation, now I'm down to 3. I did that by sliding FBC up to point C. That's on this line of action. So when I'm doing moments, I can put it there if I like. Okay. All right. And that gets me 3712 again. All right. So we're good with that? Okay. How about the next page? This one's a little bit ridiculous, but I just want to use it to show a concept here. Let's find the force in LH. Thing's a little crazy, isn't it? We got to find LH first. I think it takes some time, but I think I found it. Here we go. LH, right there. Okay. All right, now, here's how this is going to go. I'm going to look at that thing. I go, okay, I'm going to make a cut. All right. Well, let's see. Before I jump into this, first thing I'm going to do, I'm going to look for zeros, because they're kind of important to find because they can simplify what I'm trying to do. You see any zeros in there? Okay, yeah, that's a 0. There's one other.
It looks like either I or J, N.
Yeah, this guy right here. Okay, so looking at joint N, you can see that 0, and looking at joint K, you can identify those as zeros. So it's helpful on these hard ones to identify the 0 forces and get them out of there, because they declutter things up sometimes, okay?
Those are zeros because of the T?
Yeah, they're both unloaded T's at N and at K. And at N, it's got a good bit of an angle there, but so what? The angle doesn't make any difference, okay? All right. All right. So now what I'm going to do, I'm going to say, okay, I want LH, or HL, or whatever the heck it is. I'll make a cut like that. That's the obvious thing to do, but look what happens when I do that. I get 4 unknowns, don't I? Dang it. It's too many unknowns. All right. So now we're in a bit of trouble. So that's called a K-truss there because of that, that V, kind of that L-I-M thing. That's called a K-truss there.
You could do a slightly weird cut.
You could, yeah. And that's my point is there's different ways you can approach these, and and I'm a little bit short of time, but there's some other ways you can do these. You can get a little creative, which you could make a cut like that. Yeah, and you could take a moment about J. That's one way to solve that thing. Okay, you could do that. And so the cuts don't have to be straight. The only rule on the cuts is, well, there's 2 of them. One is they can't go through a joint. But the other rule is they got to go all the way through the truss, too. You got to cut through. So that's one way to do that. Now, there's another way to do it, too, that I'll point out. I'll make a cut. So when I get into a situation like this, I tend to ask myself, okay, if I make I need that cut number 2, as I'm calling it. eventually to get LH. Now, actually, if I don't, I'm kind of not going to do that fancier way I just showed you, okay? So if I'm going to use cut number 2, I got to find one of those 4 things I've cut through independently. And I bet I could do it if I make cut number 1. Okay, now on cut number 1 there, what I notice is I can solve for JG pretty quick, can't I? I can take moments about H and solve for JG. So when I make cut number 1, everything's radiating out of H right up here, except for this one. The IN I found to be 0. So I can run up there and take a moment about H, and I can solve for JG pretty quick. It's 14,933. Tension. Okay. Now, once I've got JG, I can jump that to the other side and see that's going to equal JM, isn't it? Because I've got a simple T joint there. Not much going on. I can do a sum of FX at J and jump it over to JM. And once I know JM, I've independently found one of those 4 unknowns. I've only got 3 left. And then I can go ahead and knock out the one I want, which is LH. So you could go with these in different ways. Sometimes, in a more complicated example, you might need more than one cut. Sometimes you might need kind of a crooked, jagged sort of cut. There's different ways that you can do these. And I just want to point that out to you. All right. We got just a couple minutes here, like 2. So, see, I can just go there to J and do a cut out joint J. And that is method of sections. I'm just cutting a joint out like that. Solve for J, and I'll get that JM is 14,933. And once I got JM, I can do a moment about I, and I can solve for HL on the top. A little complicated there, but I just want to point that out to you, that you can employ, multiple cuts to find out what you want to find. All right, let me get you some of these section ones to practice on. About 311, 12, and 13. Now, those will be due with the test, because this is the last bit that the test covers. So those are due Monday. We'll go over them quite thoroughly. I don't want you to have them turn them in Friday. I want you to have them over the weekend. Is why I'm making them due Monday. Okay. And that's the 20th, which is when our test is, right?
Is this going to be something on the midterm?
Yeah, this is the last bit that could be on the midterm.